Okay, today we were going to look into second part of transistor scaling. Today we will talk about 130 nanometer transistor, interconnect a little bit, not too much about interconnect. This series will be on transistors, devices. I might do another one on interconnect. But then after 130 nanometer transistor, I will look into short channel effects, why it's a problem and how it becomes a problem. So let's look into a 130 nanometer transistor just to give you an idea, okay, what kind of dimensions or what you're looking at. Okay, so 130 nanometer came into production to around 2000 2001, and I explained last time that starting maybe 250 nanometer, shrink was a further several shrinks were done within a process node. So 130 nanometer, the smallest channel length available was 70 nanometer. So let's look into why it got like that. Okay, all right, this is that transistor. So far you have looked at my hand-drawn beautiful transistor, but actual transistor is like this. This is the gate. The silicon dioxide insulator, a dielectric. You can't even see even in this picture. It's so tiny, and I'll show you a zoomed in picture of that in a little bit. And the gate length from here to here is 70 nanometer, and this is 130 nanometer process technology. Okay, this is a spacer. I think we talk about why we do this, but hold on for a sec. Okay, this is a spacer. This is not part of the device, just done there to in order to enable a better ionization or doping at this level. Okay, so it's for more for manufacturing. Then you probably be thinking, well, I already sketched it. If you were thinking, where is a diffusion? So without this, okay, let's look into that. That's the picture. Where is diffusion? Diffusion you see in this picture. Which color I want to give it? I want to give it this color. You see this little bit, this whitish thing? Let's assume we don't have that. Say we did the transistor. They started manufacturing transistor with this type of source and diffusion, and the reason is short channel effects. But let's if it was our old good friend diffusion, it will be like this. On the other side will be like this. Wow, I went a little bit down. Can I move it? Yeah, I can. Okay. So this is our source, this is our drain. And this is dielectric somewhere. What is this? What are these black things? These black things are silicides. I think I typed those in one of the previous videos too. These are contacts. This is a contact to gate, this is a contact to diffusion area. The reason for this is to provide a low resistance contact, because if you can connect a wire directly to this one, the resistance will be higher, current will not pass through the two surfaces. So this is just to ensure resistance is low. So you see how the if I rub everything out, how small is this channel compared to now that diffusion? Just this one. You can see that, okay, now, okay, how is it going to work when you apply a voltage here? There's a high voltage here. What's going to happen? I think you can guess that right now. What could be the problem with the short channel? But I'll explain you those in a minute. So, yeah, I just explained that. So you will see after I explain the short channel effects, I will explain you what are the things from 500 nanometer to 130 nanometer and beyond were done Beyond, some more things were done, but the things which were done for these process nodes, one of the things was this, that kind of gave a diffusion, this type of shape. But let's not worry about that. I think this thing explained the same thing I already explained. These are low series contacts, and these are silicides basically. Okay, this explains a little bit in three-dimensional way. The same thing is up there. So this is a NMOS, it's a P-well, right? And this is that diffusion, and this is the gate width. This is length. You see the diffusion. Those silicides, these pinks are the silicides, and those spacers are silicon nitride spacer. The purpose is I can't make this smaller than this to in order to grow this. You see this type of low LDD area. You know, this whole purpose was there, and also create a little bit of overlap, which we will talk about. Okay, you must be thinking, all right, silicon dioxide, which is somewhere around there, all right, somewhere around here that you can't even see, maybe that black thing. And on 130 nanometer, this is the width, depth of it, yeah, width of that dielectric, and it is about 1.5 nanometer. How small is that? One size of one atom silicon dioxide is 0.7 nanometers. So you're literally talking about only 5 layers of atoms already at 130 nanometer. And this is the thing that we want to make smaller with every process node. And that was the usual way of scaling. You make the transistor length smaller, make this smaller, so that you can reduce this capacitance and you can have a better effect on this surface close to silicon dioxide. But the problem is small. Well, I don't know, I'll talk about those, but your electrons can really penetrate here, kind of have a tunnel effect. Anyway, we'll soon see, you know, what kind of problem came as a result of that. So still talking about our friend 130 nanometer process technology. Came around 2001 in production. At that time, there were 6 metal layers. Okay, this is a picture thinking from the, how I can say it, from the front of the die to the back. Okay, so these buildings that you can see, actually die's base is here, the top here. This is the cutting the die and seeing inside the die, not from the top, from the front. I don't know how to say that. Okay, so look here. Where is not used then? This is our gate. Okay. Wow. Yeah, this is our gate. This is our channel. This is our diffusion. This is the contact to diffusion. Okay, makes sense? Makes sense or doesn't make sense? Yeah. These are those shallow trench isolation to separate one NMOS. Where is that? So these guys, to separate one transistor from another transistor. So look at this, even at that time, and now we are in 2024. So look at that, how small is the friend transistor here, and then you have this metal one. This is the via. Think like there's a metal was connected all the way to the top and going into my screen. So there's a via, another metal, via, metal, via, metal, via, metal. You see the sizes of some of these top layers? They're not like this. I think I explained during the interconnect material what was the reason for that. But just to give you an idea of how that building structure looked 23 years ago when I graduated. Okay, now we come into short channel effects. All right. So what happened here? Something happened here. Okay. So this is the long channel. When we say long channel, this is what really meant that look at the depth of the diffusion areas and look at this channel. This is pretty long. And this used to be case above 500 nanometer or maybe close to 1 micron. But as we got smaller, we are a bit like this. You have already seen the transistor. I don't need to draw this again, but it's basically, sorry, I don't know how I missed this. It's the same thing here. And then we have, oops, not that much. Okay. So it's the same thing here. Sorry, I don't know how I missed this one. But now our channel is extremely small, but you don't need to look into that. You have already seen here how our channel is now so small compared to the diffusion region. Now that's a problem, because all the things that we said, we have a nice current flowing through it, and then we have a nice control from the gate. We can turn it on when we want and effectively, and we can make a smaller transistor, channel smaller and still have a nice improved delay, and we have a good control on the off. It's no longer the case. You have to do some extra thing. So before we were doing what we decrease in the length and the oxide thickness we were reducing, and we would get this improvement in delay. But 500 to 130 nanometer, you have to start doing some additional thing. You're fighting with the effects of short channels. So these called short channel effects. So what is this? Let me explain here. Oh yeah, I think I copy pasted this thing, came over here. But anyway, forget about it. That's the same transistor. So let me explain you what's happening here with the short channel. So your length channel is here. Your diffusion is this. What happens now? Initially what you do is you apply a VDD here. Supply voltage was made smaller with every process technology, but not at the same rate as the length. Okay, so the scaling in the supply voltage didn't come like this. It came more like this, because reducing the supply voltage has a big impact on the delay. So you don't want to get all the benefit of the delay improvement through reduction in the length of it and then waste it with this one. So instead it was brought down. Early they would not want to bring it down, but the dynamic power, the switching power was highest, and they had to reduce it because we were increasing the frequency. So we were switching the transistor a lot more, and this time we were putting for the same place a lot more transistors. So switching power was a major concern. So voltage didn't go as down. So what's the impact? So the impact is, okay, in our good transistor, a nice gate. This is the field that was really more interesting for us when transistor is off. Doesn't matter how much voltage you apply. All we said, okay, if the gate to source voltage is not VT or above VT, the channel inversion will not happen here, and I'll talk about in the threshold. Well, I will revise you, even though all threshold voltage is already talked about in transistor section. But in a nice or good old transistor was a nice switch, and unless we apply this voltage to threshold voltage and then above that, this channel will not turn on. And when it's turned on, then we apply voltage here, and then our friends sorry, I'm calling everything friend, but these electrons start flowing here. That's it. But when you are talking about channel length this compared to the source and diffusion region this much, keep in mind now you have this is the reverse bias area was, and when we increase, you remember from PN junction, or what I meant, I think I didn't explain PN junction diode. When you in the depletion region, when you apply higher voltage, This is big. This depletion region gets bigger actually. And now I'm exaggerating. I think if you look at some of the picture, it's really like that. And this one increases. So there is a very strong voltage applied here, positive, and the electron feels a strong pull that side. In such a way, this voltage can be so strong, it can really drag the transistor from here even when there is no kind of channel created. There are electrons here, right? There are some electrons here. This is so strong, it really around here, it can start pulling it because this region is getting smaller and smaller. Now this dragging, what it happens is that threshold that we had, okay, unless we apply a gate voltage, now you don't need that much gate voltage. See, the strong inversion that happen, it doesn't happen abruptly, it starts happening gradually. So little bit gate voltage here will create some electrons here, a channel and an n-type material here, that this strong voltage will start pulling it all the way here. And because of that, this transistor was not behaving the way we wanted. Its threshold voltage is disturbed. Its current, because now it's a strong movement here, it doesn't mean the more current flow. They start in scattering, they start hitting each other, collisions happen, and actually current reduces. And because threshold voltage lowers now, because we can turn on the transistor pretty easily, pretty quickly, the whole new phenomena happens, which I'll talk in a minute. And so this is the short channel effect. This is impacting everything: current, speed, threshold voltage, and therefore the off current and on current and everything. So overall our I on, the on current, which really we want to increase every generation 30%, that actually decreases. The threshold and the saturation starts happening earlier on and with a smaller magnitude. We will look into that. I off increases. You have a less control in the channel. Your threshold drops. And so these are the problem of the short channel effect. So let's stop here. In the next video, I will go a little bit further into short channel effects because those were important part of not only from 500 to 130 nanometer but beyond. But yeah, let's talk more about those in the next video. That's it for now. See you next time.